We used differential notation briefly when we were working with arc length. This is when we used dx, dy, and dz to represent a little bit of movement in the x, y, and z directions, and then used dl to represent a little bit of arc length. This differential notation has some other applications that we're going to look at here. Given a function f of x, y, we can use the tangent plane near the point x0, y0 to get an approximation of its value at nearby points. While we can use a generic xy to denote a nearby point, we want to pick a notation that emphasizes the nearness. So we're going to call the nearby point x0 plus dx, y0 plus dy, where we implicitly view dx and dy to be small values that represent the shift in the x and y directions. When we look at the linearization, we see that it can be broken up into two pieces. The base value is f of x0, y0, and the rest of it is the change, which we call df. When we move the point by a small amount, the function f changes by a small amount from its baseline value. We can also see that if we substitute for x and y using the dx and dy relationships, that the difference terms simplify. Putting it all together, we get df equals this quantity. In Leibniz notation, this is written as df equals partial f partial x dx plus partial f partial y dy. Remember that since we're using a linearization, we're making an approximation of the change of f and not the true change of f. For the true change of f, we would use delta f. This is a subtlety that we don't need to dwell on here, but just remember that differential notation is implying that we're using an approximation of some type in the calculation. Let's look at an example. Suppose you have a machine that cuts rectangles. It's supposed to cut rectangles of width 20 centimeters and height 10 centimeters. However, because of machining tolerances, the width can be off by as much as 0.2 centimeters, and the height can be off by as much as 0.4 centimeters. We are going to use differentials to approximate the potential error in the area. In the sketch, we've shown dx and dy to be positive values, but they could just as well be negative values. The shaded area is just a representation of the possible error, which we're going to approximate using differentials. The formula for area is a equals xy, where x is the width and y is the height. We will first calculate the derivatives. Then, by using the differential, we can compute the error estimate dA equals y dx plus x dy. We can then substitute in our values to get that dA equals 10, which shows that the area can be off by as much as 10 square centimeters. As a student, this sort of problem always confused me. Why not just use the area formula and get the exact maximum error? Why even bother with differentials? In practice, you don't always have a formula. This means that the calculation of the derivatives is often the result of a numerical estimate and not an analytic derivation. And so in more practical settings, you simply don't have access to those things. Specific to this problem, we can absolutely get a more precise answer. But that's just not the exercise we're being asked to do. Problems like this, where you have an exact formula from the beginning, are really just an artificial construct to provide an opportunity to practice multiple skills. The first skill is just practicing how to read and interpret word problems. Then there's the ability to calculate the partial derivatives correctly, and the last skill is to understand the use of differentials and linearization to estimate the change of a function. So don't be like me and don't overthink it. The main ideas here are that you can use the linearization to estimate the change of a function if you change the inputs by a small amount, and that this can be represented using differential notation.